prove the well-known result that for a given launch speed, the launch angle of 45 degrees yields the maximum range. Do y'all know that? If you want to launch something as far as you can, if you're starting and ending at the same height, you need to launch it at 45 degrees, right? Y'all think it kind of makes sense. If you launch it too low, it won't go as far. But also, if you launch it too high, it also might not go as far. But if you launch it at 45 degrees, neglecting air resistance, you would get the maximum range. How could we prove that? How could we prove that? We could write an equation for R over any theta. So I'm just going to leave theta in there. And so on my X equation, I'm going to have, cosine theta in my X equation. For my Y equation, I'm going to have sine theta in my Y equation. And eventually we could solve for theta. But write an equation for R. Once we have an equation, how can you find the maximum or minimum of an equation? Derivative, yeah, we could take the derivative. What? Yeah, set the derivative equal to 0. So I will post this and show you, but you know what we do? We break it up into X and Y. We use SF equals SI plus VIT plus 1/2 AT squared. We use SF equals SI plus VIT 1/2 AT squared. And it's really cool how it works out. And we get 45 degrees. We get 45 degrees. And so we'd actually get this right here. We would get R is V initial squared times sine of 2 theta over G. And so our max, when would this be a maximum? When theta is equal to 45 degrees, right? Because sine goes from between 1 and 1. And so the maximum that this term could be is 1. So the maximum is V squared over G. So we would prove that 45 degrees gives us the maximum. And we'd also prove that the range is V squared over G. The maximum range is V squared over G. All right.